In this video, I want to show that if I is an ideal of a ring R, and if R inverse is an I, this implies I is equal to R. So what I'm going to do is I'm going to let R be an R and R inverse be an I. Now, the definition of an ideal, which I've included, says that for any element in I and any element in R, when I multiply them, it's going to be within I. So I'm going to just go ahead and do that. So R times R inverse is going to be in I. Well, let's simplify that a bit. Let's simplify this piece. This piece is going to equal, well, R times the inverse, anything times the inverse of itself, is just 1, and that's going to be within I. But if 1 is the element of an ideal, so now I've gotten a new idea. So I've gotten a new thing. I've got a new element in I. I found 1 is in the ideal. And let's see how I can use that. So now I'm going to come over here and do another thing. I'm going to say, let's look at 1 times R. Well, 1 times R is just equal to R. And by definition of an ideal, 1 is in I, and R is in R. So that must mean that this is another thing that's going to be in I by the definition of ideal. And so R is in I. Now, since R is an element of I, this actually implies that I is equal to R. This makes sense because if this wasn't true, if this piece was not true, then what would happen is you would have something like I, or you would have had two elements that you multiplied together. You would have had some item in R, any element in R, just one, that when you multiplied with the element in I, it was no longer an I. But since 1 times R is just R, this would have to ask you to pick an element not in I. In this video, I'm going to show that if I is an ideal of ring R, and if R inverse is an element of I, this implies that I equals R. So I'm going to let R inverse be an element of I, and R be an element of R, and I be an ideal of R. Okay, those are all the things that I was given. So now I'm given this piece, these elements, and the definition of an ideal is that if I take any element in I and any element in R, when I multiply them, they're going to be within I. So I'm just going to do that. So I'm going to take R inverse times R. Well, that's going to be in I. That's pretty basic. But what's R inverse times R? Well, R inverse times R is really just 1, which if you think about it, I'm going to mix the imply symbol. R inverse times R, well, that's just saying 1 is in the ideal, because this is just a 1. This whole thing is equal to 1. So that implies that 1 is in the ideal. So now I found a new element in the ideal. I haven't figured out my solution yet because I haven't proved that they're the same, but I'm going to use this. I'm going to try multiplying again. So I'm going to do 1 times R. I chose an element in I and an element in R, well, that's going to be equal to R. And since this is an element in I, and this is an element in big R, this must mean this is an element of I by definition of ideal. Okay? And since this R is the same as this R, this implies that I is equal to R. The reason you can say that this statement is true is because if you think about it, if you choose any little r in big R, so choose anything, it has to also be an I. And the only way that that subsets, since I is technically a subset of R, since by definition I is a subset of R, the only way that the subset can be complete, or the subset can be the same size, or have the same number of elements, is if they're equal. So what you can say is, so you can actually say something like that. It depends on what your professor wants. When I took this course, this was a completely fine proof because it came by following along. But if you think about it, it makes a lot more sense. You could add more words to it, but that really depends on how well you are explaining things and whatnot. I hope you like this. If you have any questions, please comment below. If you need any clarification, please comment below. If you have any questions you want me to try to tackle, please let me know. And thank you for watching.